So welcome back for the week 2, of course, Open Run, the future of radio access network. Okay. Hi there, I'm Richard Matias, and I'm one of the course co-creator for the Asia Open Run Academy. And this online course is a collaborative effort of DICT and Asia Open Run Academy, and it is made possible by the American people's support through the United States Agency for International Development, or USAID. Today, we have two of Asia Open Run Academy's most distinguished lecturers, which will cover one of two topics. So I'd like to introduce our first speaker for today. She's a full-time academic staff at the Electronics Engineering Department of the University of Santo Tomas, Manila, Philippines. She is teaching several undergraduate courses on communications and computer networks. She is also a PhD candidate in the Department of Electronics and Information Engineering at Hong Kong Polytechnic University. Her current research is focused on IoT, wireless sensing, machine learning, and related topics. She is also one of the ORA, or Asia Open Run Academy, course co-creators who developed the two courses, namely Deep Dive into ORAN Architecture and the RAN Intelligent Controller. So ladies and gentlemen, engineers of the Philippines, please welcome Engineer Jocelyn Mariela Reyes.
Hi, hello, good morning. I guess we can now start now. For the first 2 hours of today's webinar, we'll have a discussion on the second course of Asia Open Run Academy, which is entitled as Deep Dive into ORAN Architecture. Okay, so previously in the last week, you were able to be introduced to ORAN architecture, or rather to Open RAN. So hopefully some of those knowledge will be carried over so that you can easily understand the next slides or next lessons that we will be discussing. Okay, so in this particular course or this particular module, we'll have the deep dive into ORAN architecture, and this covers the actual architecture of ORAN and some relevant specifications. So we'll discuss first the architecture evolution of radio access network, which was also mentioned in the previous lesson or previous webinar, wherein we started to disaggregate the hardware and software components. Originally, all of them are in one device, then slowly they are being separated because of virtualization. Okay, so Open RAN considers not only Open Radio, Remote Radio Unit and BBU or baseband unit, but also the open interfaces. Because all of them are now open or not proprietary, it is possible to implement or deploy deployments or implementations that have different vendors. It's no longer basically just one vendor that handle all of them. We can now interoperate them. And then this course also expounds on the 4 main functional components in Open RAN. We have the distributed unit, the centralized unit, the near real-time RAN intelligent controller, SMO with non-real-time RIC. Okay, so don't worry, we'll go over all of these concepts later, and hopefully we'll get more understanding in the ORAN architecture. By the end of this webinar, or by the end of the course that is being offered by Asia Open RAN Academy, the learner must be able to summarize the evolution of the RAN architecture and define these different RAN evolutions, DRAN, CRAN, VRAN, and ORAN, and then also identify the hardware interfaces of the ORAN architecture. Okay, so you should also have access to the Terahertz learning platform, where some of the learning activities are present there as well. And the recording of this particular module will be made available there as well. Okay, so ayan, with that, let's also go into the outline of this presentation. So there will just be 6 parts, and after the 3rd part, we'll have a break from the webinar, and we'll have some learning activities to be hosted by Richard. Okay, so we'll go over the RAN architecture evolution, and then finally the overall architecture of ORAN and some specifications, and how ORAN complements the 3GPP standards and other industry standards like the OSI model. And then let's go deeper into the different functions and nodes of 3GPP and ORAN, and the relevant interfaces in the ORAN architecture. Because not only are the hardware open, but also the interfaces connecting these hardware. And finally, some basic implementation options and deployment scenarios involving the ORAN architecture. Okay. Okay, so first of all, let's start. We are already aware that in Philippines, there are several mobile network coverage, several different generations of cellular technologies. We have 2G, 3G, 4G, and also now we have 5G. So in the previous discussion or previous week, Richard gave a link to the NPerf map, wherein you can access the different network coverages depending on which telco provider that you selected. Okay, so in that mobile network coverage website, you can see up to which point the different technologies can cover. So these are just some snapshots of in some of the cities in Philippines. So in Davao, in Manila, and in Cebu. Okay, so but take note, these snapshots are only in the roads. So of course, we know that the mobile network coverage of each radio station, base station of the cellular systems would have a larger coverage. Usually, it's like hexagonal cells when we plan that. But in this mobile network coverage, they only show the roads because that's where they drive through and measure the signal strength. Okay, so in Philippines, we now have some 5G connections in several places, although mostly it's really 4G plus. So it's really important that we start studying Open RAN, because Open RAN has started development since 5G has been deployed. Even though it is mostly for 5G, there are also some efforts in implementing it for 4G as well. Okay, so you can find the link to this website here at the bottom below. You can try it out so that you can just have an interactive activity in this lecture. Okay, so first of all, just a brief review. What is radio access network? Oh, sorry. Radio access network. So in the telecommunications overall scheme of things, this radio access network is the network connecting the core network to the end user. So we have the core network here, and then the core network is connected to the access network via the transport network. And then the access network provides the radio frequency function towards the user equipment. So this is where the antennas are placed, and then inside the access network there are other equipment like the baseband units and so on. So of course this is like the base station, but not only the base station but also other different equipment that will be used to ensure that the end user has access to the service provided by the telco. Okay, so over the years, over the different generations, there are various names for the radio access networks. So in 2G, for GSM and Edge, we have the GSM Edge Radio Access Network, or GERAN. And then under GERAN, or inside GERAN, we have the base station controller and the base transceiver station. So this is what we commonly use, or this is the terminology that we commonly use when referring to base stations. But in 3G and 4G and 5G, we have different RANs, basically just a different name because there are different specifications for them. So in 3G, for the UMTS, we have the UTRAN, which is the Universal Terrestrial RAN. So that's for 3G. And then inside the UTRAN, we have the radio network controller and the node B. So it's node B for 3G. And then for 4G, we have the LTE or long-term evolution. This is the evolve UTRAN. Then this is the base station or the base station component is known as the E node B. Then for 5G, it's 5G RAN, and then the base station component is called as G node B. So the terminology for the RAN varies depending on the considered cellular technology generation. So the RAN itself is the general name for the access network equipment for cellular networks. So if we hear RAN, then we'll know that it's basically the access network for that particular system. Okay. Okay, so for the RAN architecture evolution, some of these slides were already discussed in the previous lecture, but we'll go over them again so that as a form of a review. Okay. So first of all, the reason for having the evolution is that the different subsystems of each part started to split, started disaggregation. Originally, the servers, the devices are dedicated for a particular application, basically just a traditional setup wherein the devices itself have their own functionalities. But because of virtualization, because we can now separate the hardware and software, now the core network hardware and core network software can be separated from each other. That means we can just implement them as some form of virtual machines running on a cluster of servers. It would help. It would help in the utilization of the hardware components so that it will be maximized, and as well as if there is a need to have redundancy in the network, we can just create a separate virtual machine on top of the whole physical architecture. Okay, so anyway, so we have the core network again. Then we have the transport network, also known as the backhaul. It connects the core network to the access network. And then in the access network, there are also hardware and software components that we will cover a little bit later. Then the radio access network provides the coverage to the user equipment or the end user. Okay, so for Open RAN, the focus is more on the disaggregation of the radio access network components. So we're going to just deal with this portion because this portion is where we need to cover certain areas. So this aggregation also offers less capital expenditures for the mobile network operator, which in turn hopefully will help really add more coverage to the different cities. Okay, so of course, the concept of hardware and software disaggregation is not limited to telco. It started long time ago, and even in the different hardware, like in mainframes, in servers, in switches, and others. Everything started to disaggregate because it's cheaper, or rather it's more cost effective that way. Instead of having dedicated servers, dedicated devices for just one application, it's much better to provide virtualization efforts and maximize the resources of the hardware. So there are already virtualization efforts, like for example, VMware. It's a cloud computing platform virtualization. But we're not going to deal with the virtualization component, but rather we'll be focusing more on the radio access network. But this is the motivation behind the disaggregation of the hardware and software. So the motivation behind the separation of the hardware and the software. Okay, so in a traditional RAN, for example, in 2G and early phases of 3G, the baseband unit and the radio unit are co-located. So that means they're in the same place or same position. And then, for example, in this case, so the baseband unit and the radio unit They are inside this box wherein the signal processing, the RF equipment, the network access, and then the long RF cables are in the same place. Okay, so but this TMA is also known as a top-mounted amplifier. And the problem with this kind of setup is that there is attenuation loss or signal loss along this line. Okay, so from the baseband unit, from the radio unit to the TMA. Okay, so in later phases of 3G and also in the rollout of 4G, now we have the remote unit, the remote radio unit or RRU. It's now implemented near the antenna. And then this RRU is also called as RRH or remote radio head. Okay, so in this case, the signal processing and network access is at this portion. And then the ADC and the ADC and DAC now are now in the RRU. It's nearer to the antenna, so there is minimal losses, and also there is now this CPRI or CPRI. It's a front hall interface, so it's the one connecting the interface between the RRU and the BBU. So the BBU is here, the baseband unit is here, and then this portion, the interface here, is the one connecting to the RRU. It's one of the widely used popular interface for front hall connectivity. Okay, so you can see the remote radio unit is a hardware component in charge of the RF and the DAC ADC. And then the baseband unit is still processing the signals and other functions. In this case, since we have separated the radio unit from the BBU itself can drive several RRUs. They don't necessarily have to be co-located at the same base station, but they're now separated. The reason for this is to move it closer to antennas and minimize signal loss. And now we have this front hall defining the interface between the two. It is now using fiber instead of copper, so to have less signal losses. Okay, so this is the traditional RAN. This one is the non-split architecture, and this is the split architecture because here you split the radio unit and the baseband unit. Okay, so the same concept, but just a different diagram. The BBU can handle several radio units, and then we have here the CPRI, which is the interface connecting BBU and RU, and also we have this split architecture wherein the BBU is separated from the RRUs. Here it was inside here. Okay, so the RRU is close to the antennas now. Then of course, the BBU is connected to the backhaul, and then the backhaul can be a microwave or a fiber. This connects to the core network. Okay, so this is the traditional architecture. And then for the next kind of architecture or the next evolution of RAN, we have the centralized RAN, also known as Cloud RAN. In Cloud RAN, the BBU functionalities are found in the central office. And then there is just going to be an optical distribution network or ODN that is deployed as the front hall connections. And basically the BBUs are pooled in the central office, and the optical distribution network is in charge of sending the signals that will be later converted, later be applied to the ADC and DAC at the remote radio head or remote radio unit. Okay, so the RRH might be replaced by active antenna arrays and antennas with integrated RRH. Okay, so this one, in this case, the front, there are limited area. This is limited to areas where there are access to fiber connections. And the problem with this is the CPRI, the hardware components are still proprietary. So even if you are able to pool the resources, the BBU on the same central office, there is still an issue of vendor lock-in, especially because the front hall is a proprietary interface. But this started the concept of pooling, the pooling of the resources. You can just host all the BBUs now on the central office instead of it being on the cabinet at the base station. Okay, so there is also another form here, the virtualized RAN. This is also known as the virtual RAN. In this case, the BBUs are commercial off-the-shelf hardware, but it is running proprietary software. The proprietary software are virtualized network functions or VNFs. Okay, so the BBU functions, the virtual functions, is now separated from the hardware itself. You can just buy a commercial off-the-shelf hardware and then run the proprietary software. So that is now where we start to have an open hardware. But still in this case, the front hall interface is still proprietary. So this particular VRAN is not yet an open RAN because the interface is not yet open. It's still a proprietary software, a proprietary interface. So whenever you change one equipment, then you have to also change the other equipment because the interface is proprietary to that vendor. So it's not cost effective in the perspective of the mobile network operators because you have to overhaul the devices, you have to change the whole setup. Okay, so here now just a review of the different radio access networks architecture so far. We have the DRAN, the traditional RAN. In this DRAN is we have the baseband unit here, and then the front hall is here. The back hall is to the core network. The CRAN or the cloud RAN is where we can now have the several BBUs pulled together. And then here we have the VDU and VCU, basically some components of the baseband units. It is now virtualized on top of the server. Then for Open RAN, now we'll have something similar, but the main difference is that the front hall interface is open. There is a defined front hall interface that is not proprietary. Okay, so as a summary of the RAN architecture evolution, this is how it, So first is there is a traditional RAN. In that case, by the traditional RAN or in DRAN, there we have the non-split architecture. This is involving the RRU and BBU. They are co-located on the same site. And then we have the split architecture, the RRU and the BBU. They are connected by CPRI or CPRI. This is a proprietary interface. Then next is the centralized RAN or CRAN. The BBUs are pooled in a centralized location, like for example, the central office. And then the site only has antennas and the remote radio unit. There are two options under CRAN. There is the split BBU, non-split BBU, and the split BBU, wherein the BBU is now split into two different components, the distributed unit and the centralized unit. So the functions of these two may vary, which we'll discuss later. But essentially, the BBU has several functions from OSI layer 1, 2, and 3. And by splitting it into distributed unit and centralized units, we can assign certain functions to the distributed unit and to the centralized unit. And then for virtualized RAN or VRAN, the BBU functions are virtualized. So they are now VNFs running on top of a commercial off-the-shelf server. So it's like running cloud functions. So that way, you just have to buy a commercial off-the-shelf server And then if you have to upgrade, then you can just buy any server, no? Not necessarily have to buy from the same vendor. Then for Open RAN, no, the Open RAN is the remote radio unit is COTS-based hardware or a commercial of the shelf-based hardware. DBU is also COTS-based hardware. Both of them are basically open because it's any server that can run the functions, can run the virtual functions. So the VBU functions are virtualized. The software is virtualized and it can be proprietary, but that's okay because the hardware are open. And then the front hall interface connecting the RRU and DBU is also open. We have an open interface instead of the CPRI. So later in this lecture, we'll have also some discussion on the different interfaces. Okay, so the RAN functions now are separated into three. We have the radio unit in charge of the RF component, and then the BBU is now split into DU and CU. Okay, so the functions of each of these two is defined by 3GPP. This is called as the functional split, which we will also cover a little bit later. Okay, but in this slide, we're just going to explain the architecture evolution. Okay, so also this is another way of looking at the architecture evolution. So for traditional RAN, you have everything proprietary from the remote radio unit, the BBU hardware, software, and the front hall interface. All of them are proprietary. And when we go to centralized RAN, all of them are still proprietary, but we started using pooling to pool all the resources in the same location and use a distribution network to connect the BBU and the RRU. In the virtualized RAN, it started the movement towards open, wherein the BBU is hardware now that is commercial off the shelf, but the software is proprietary. And then finally in Open RAN, the remote radio unit is a commercial off the shelf device or the software defined radio. And then the hardware of the BBU is a commercial off the shelf server. And then the commercial off-the-shelf server is running the VNFs or virtualized network functions. And the front hall interface is now open. So later we'll look into the different interfaces and which one is the open interface. Okay, so basically the idea of Open RAN is that there is a virtualization of the different functions of the baseband unit and the remote unit. The standards should be open and interoperable. That means if you buy a different device, then the virtualized network functions can still run on them. And also there is this term called the functional split defined by 3GPP. So basically this defines how the BBU functions, how each component of the BBU functions, what are the particular protocol that will be running on them. Okay, so more on that a little bit later. Okay, so hopefully that gave you a review of the architecture evolution. Those different architecture of RAN were already discussed in the previous lecture, but this is an overview again to provide you with a background of the architectures. Okay, so now let's proceed to the next subtopic, which is the overall architecture of ORAN and some other specifications. Okay, so we are already aware that the RAN is this component here, the access network, and the main RAN components are the RU or RRU, remote radio unit, and the baseband unit or BBU. Okay, so the connection from the BBU to the RRU is the front hall, and then the connection from BBU to the core network is the back hall. Okay, so also in Open RAN architecture, this is just an overview of the Open RAN architecture. there are other components, no? Not only the RRU and BBU, but it's now split. No? Basically, the BBU function is composed of the centralized unit, this part, no? The centralized unit and the distributed unit. No? Okay, so this is the BBU now. It is composed of the centralized unit and the distributed unit. No? And then the radio unit, of course, connected to the baseband unit via the front hall interface. And then there are other components, no, in the ORAN architecture. Okay, for example, there is a SMO, or System Management and Orchestration. It is responsible for RAN domain management. Basically, since there is now virtualized network functions across the different radio access networks, there should be a centralized device or centralized function or component in charge of managing all of them. So it's like the one managing the control planes of the different components. Okay, and also there is the near real-time RAN intelligent controller, or RIC. This one supports the tasks that require less than 1 second of latency. So also this specific RAN intelligent controller actually will be covered later by another speaker, and also next week as well. So just keep in mind that the RAN intelligent controller is like a controller of the radio access networks. And one part of this is the near real-time RAN, near real-time, so less than 1 second of latency. Okay. So since the baseband unit is now separated into distributed unit and the centralized unit, there is now a different interface connecting the two components. This is the mid-hall interface. Okay, so the mid-hall interface is between the DU and the CU. This mid-hall interface is called F1. It is defined by 3GPP. Okay, so in this overall architecture, the O in front is just means open or ORAN. So this is open distributed unit or ORAN distributed unit. This is an ORAN radio unit. This is ORAN centralized unit. Okay, so this is just an overview of the whole architecture involving the different components of the ORAN architecture. Okay, but in the ORAN Alliance, they define a much more complex architecture, overall architecture. But before showing the overall architecture, let me just also describe some of the other components that were not seen in the previous slide. For example, we already have the SMO here, the Service Management and Orchestration Framework. Inside it, or rather within it, is the non-real-time RIC. Non-real-time RIC is the RAN intelligent controller that supports tasks that require greater than 1 second of latency. So it's different from the near real-time RIC mentioned earlier. So non-real-time, greater than 1 second. Near real-time is less than 1 second. Okay. So what else is new? There is also an OCloud or ORAN cloud infrastructure where the cloud native virtualized functions are running. Okay, so basically the ORU, this is the radio unit, the ODU, OCU, OCU here. This is the BBU, this all of this. There's just a control plane and a user plane. And then here is the near real-time RIC and non-real-time RIC. So in the overall architecture of ORAN, or the ORAN architecture overview, this is basically their architecture. It not only involves the SMO, the RIC, etc., but also the interfaces connecting all of them. So which is why I first showed the components first before showing the different interface. But this is the important part. This is the heart of this lecture. This is the architecture of the ORAN. Okay. So in this case, you can see there are several interfaces here. At first, it's really complex looking because there are so many different interfaces. And you can see as well, there is a legend, the one with the gray line. This is defined by 3GPP. The green line, the straight line, is the ORAN, ORAN interfaces. And there is this dashed green line, which is a potential future interface, but is not yet defined. Okay, so this part this can be one E node B. Then the near real-time RIC can connect to other E node Bs that are open. Okay, so the near real-time RIC can basically handle several different E node Bs. So this one can be pulled and then can manage or can orchestrate the different functions of other E node Bs or other G node Bs. It is possible to have like a multi-radio access technology. You can have several cellular systems running in the whole radio access networks. Okay, so you can see this is the names of the interface. The one connecting the DU and RU is the front hall interface. There are two different planes, the management plane and the CUS plane, or the control, user, and synchronization plane. But if you hear the term front hall, that is the connection or the interface between the DU and the RU. And the connection between the CU and the DU is F1. And in this case, there are just two F1 here because one is for the control plane, the other one is for the user plane. But if you hear F1, that is a mid-haul interface. So when you say mid-haul, it connects the CU and the DU. There are just other components here to just show further the different components inside. And then we have an E1 interface. This connects the control plane and the user plane. Okay, so also there is this E2. This is the interface connecting the near real-time RIC to the baseband unit. So since the baseband unit is composed of the CU and DU, you'll have here an E2 connecting the near real-time RIC and the CU. Ayan. And also here, itong tatlo. So the near real-time RIC is connected to the baseband unit through the E2 interfaces. Papansin nyo, you'll also have an E2 here kasi you also have another base station here wherein there is also a baseband unit inside. So hindi na natin makita here, but this is a representation of another baseband unit. Okay, also the connection or the interface between the two RICs is A1. Okay, and then we have here O2 connecting the service management and orchestration framework to the O cloud. Basically, the non-real-time RIC and the SMO is in charge of handling some functions that require greater than 1 second. You can have there an AI, some machine learning. So basically, the added services that can help make the whole architecture efficient. So that's why it's connected to the cloud because the processing, the storage can be done on the cloud rather than it being done on the office, the central office. Okay, but the near real time is much closer to the components, to the baseband unit, because it should be able to handle latency or the tasks that require less than 1 second latency. Like, for example, quick decisions regarding the radio access networks. Okay, so this is the most important architecture, the most important slide. This is the center of our lecture. And at first, it's really looking, it looks complex, but as practice, what we do is to really draw this by hand, create, or rather draw first the components, the blocks, and then later you draw the interface. Okay, so if you want to go back to this slide or this architecture, you can just view the documentation from ORAN website. So the docs.o-ran-sc.org/en/latest/architecture/architecture.html. Medyo mahaba, no? But if you search ORAN architecture, no, you should be able to find the image, no, that looks like this. Okay. So let's proceed to the next slide. Also, we have an ORAN Alliance Reference Architecture. Is just one way not to view the same architecture before, no? Just a different parang placement. No? So we have the SMO still, the non-real-time RIC connecting to the near real-time RIC using the A1 interface. The near real-time RIC connects to the central units of different nodes. The central units may run different radio access technologies. It can have, for example, 4G or 5G, and so on. And then the centralized unit connects to the distributed unit using this mid-haul interface, F1. Okay, and then also this two, this centralized unit and distributed unit is what we call the baseband unit. Napaghiwalay na sila when we go to the Open RAN architecture. Okay, the reason for separating them is that we can assign different functions, different protocols on them, depending on the implementation of the mobile network operator, depending on ano yung mas convenient for them. And then the radio unit, of course, the one that is in charge of delivering the service to the end users or delivering the information or the last hop towards the end user. Okay, so of course we have the front haul interface here. This is the one connecting the distributed unit to the radio unit. And if you search for this ORAN Alliance Reference Architecture, it also has a lot of information. Nagiging ganito siya. Inside the SMO, there are different components, different functions. And then also in the near real-time radio RAN intelligent controller, there are several applications there for radio connection, mobility, quality of service, etc. Kaya mas simple yung kanina, no? But here is this is what you can see, no, if you search on the internet. If you search for the ORAN Alliance reference architecture, you'll see this. All the information is given, no? And then basically may mga protocols here, no, like MAC, PHY, no, etc. So later we'll explain, or we'll go into detail kung ano yung functions applied in the centralized unit and the distributed unit. But just to give you an idea, no, ito muna, no, overview lang siya, just like the same architecture before. And then this is the more detailed architecture or reference architecture. Yeah. Okay, so again, I'll just review again. We now have knowledge on the ORAN architecture. So the ORAN architecture mostly involves the BBU and RRU. We have seen that inside the BBU, there are different components like the distributed unit, the centralized unit, no? And may mid-haul interface then inside them, connecting the two. And then the RRU, no, is the remote radio unit connected via front-haul interface. And then earlier I mentioned that the BBU, no, is parang split. No? It is a split to the DU and the CU. The DU is the distributed unit. CU is the centralized unit. So this split RAN architecture is proposed by 3GPP, found in this specification. If you Google it, or ito, no, nasa link sa baba. If you search for this link, no, the 3gpp.org/dynareport/38801, you should be able to see the definition of the split architecture. Okay, the reason for splitting this is so that you can pull you can just assign certain functions, no, to centralized unit. No. This centralized unit is the one connecting to the core network, and then the mid-haul interface, no, is the one connecting CU and DU. DU is connected still to RRU. Okay, so the specific CU and DU functions may vary depending on what we call the functional split. So in the different protocols, so they run on OSI layers, and some of the protocols that can be assigned for the distributed unit, some of the remaining protocols in the CU. Depending on the particular split, no, it rather depending on the mobile operator, no, they can decide which of the split that they will use. Okay, so what is the functional split that you have been hearing so far? So the different protocol layers will now reside in different components. The split implementations are more flexible and easier to fit, depending on the deployment constraints of the mobile network operator. So this splits are standardized so that we can have the interoperable solutions from different vendors. Okay, so the three key factors that influence the split choice are as follows. The specific QoS that the mobile network is targeting, what is the user density for the particular location, and also the transport networks, whether the transport networks can handle a certain function, or whether there is a different performance levels that are required now. Okay, so this is the functional split overview. So originally we have the monolithic RAN, or the just two components. We have the radio unit and the baseband unit. But for the RAN functional split, we now have the CU and the DU. This two is the baseband unit. We now have three different parts, the CU, DU, and RU. Okay, and then the split part is this portion here, this split here and here. So there are two splits possible. We have the low layer split, the LLS, then the higher layer split, HLS. So LLS, HLS. And it's possible to have both. So you'll have a dual split. So this split functions, this split implementations allow for flexibility and also for virtualization for the mobile network operators. So they can implement whatever they need. If they can only handle the DU components for the upper layers, then they can just have the low layer split. Or if they just want the high layer split because that's how their current systems are, then they can just have a CU and then this portion here. So they can just have a high layer split. Okay, so more on the functional split, the actual options, different options for functional splits by the next lecture, the RAN Intelligent Controller. The details for the functional splits will be discussed in the next lecture. Okay, so hopefully you were able to understand the overall architecture of ORAN so far. So in the ORAN architecture, we really had this slide here. I'll just show briefly. And this is the important slide that everyone should become familiarized. So at first, it looks really complex, but over time, if you keep seeing it and then you can draw it, you'll be more familiar with the architecture.
Okay, so before we start our second half ng discussion ni Jocelyn, let's have a Kahoot first. Okay, so I think we can start our Kahoot. So habol na lang yung iba if you were not able to join in time. Okay, so this Kahoot is composed of 12 questions. So the ORAN Alliance was formed by a merger of two different organizations. So name those two organizations. Okay, that is those are the CRAN Alliance and the XRAN Forum. Next. Question number 2. Which interfaces in the ORAN architecture are considered open? So which of the following, or which interfaces in the ORAN architecture are considered open? Since this is an open RAN, all interfaces must be open. Okay. So drop the pin on the location of X app. So whenever when we are trying to locate the X app, so it's inside the near real-time brick. Okay, here it's the X app. Okay. Number 4, it's a collaboration between the ORAN Alliance and the Linux Foundation with the goal of promoting open source software for RAN. It's called the ORAN Software Community. Okay. Number 5, in wireless telecom, the RAN gives mobile network coverage to subscribers. What does RAN mean? Okay, it's radio access network. Very good. No? Everybody get it correct. Okay, next. Number 6. In ORAN Alliance, which working group is focusing on all use cases and the overall architecture of Open RAN? So there are 11 working groups as of now. So which working group is focusing on all the use cases and the overall architecture? That's the work group 1. Okay. Number 7. Name the 2 network architecture of a 5G system. So this is one of the topics that we have discussed last week. The 2 network architecture of 5G system. Those are the standalone and the non-standalone. These 2. Okay, number 8. So this is the total cost of ownership of a network is in the RAN. So how many percent? So what do you think? How many percent of the total cost of ownership or the TCO of a network is in the RAN? So when you say TCO, it's the sum of CAPEX and the OPEX. So based from the operators around the globe, it's 60 to 65% of the total cost of ownership is in the RAN. So that's very expensive, no? Okay, number 9. Which entities in the ORAN architecture can be called the E2 nodes? So the E2 nodes are here, below the near real-time brick. So which of the following entities can be called the E2 nodes? So that's the ODU, the OCUUP, the OCUCP, and the OE node B. So those are the E2 nodes. So collectively, we can call them the E2 nodes. Okay. Number 10. This is a cloud computing platform consisting of physical infrastructure nodes that host ORAN functionalities. What do you call this cloud computing platform? That's the OCloud. Number 11, how much of the traditional RAN market will transition to Open RAN by 2030? So this is one of the vision under the Open RAN. And Open RAN is also seen to be used for the 6G in case 6G will come in 2030. So how much of the traditional RAN? So they're looking at 60% of the RAN market will transition by 2030. Okay, last question before I give you back to Josel. So in this architecture, the RRU stays at the cell site while the BBUs are aggregated into a centralized office. What do you call this architecture? That is centralized RAN.